Um, Hello, my name is Calvin Deutschbein. I am an assistant professor of computer science at Willamette University, which is in Salem, so I got very lost on my way here. This is an adaptation of my talk at the conference last year on some of the research I'm doing with my research group, which includes Jimmy Osler. I'm going to say the word Rust approximately 500 times in the next 8 minutes, and that's because I'm collaborating with an undergrad that's into the next big thing, okay? I love C89, right? I think it's a great language. So, what problem am I trying to solve? Well, I'm trying to solve two problems at the same time. I have to do something that is interesting for my undergraduate students and might get them a job when they graduate in 4 years after AI has destroyed all of the jobs. And I think one of the things that AI is going to be bad at for a long time is memory management. And I think that this Stack Overflow developer survey from 2025 that shows that Rust is the most beloved language is reflective of that. Because I've tried to write memory safe code in C, and I did not enjoy that process, even though it is possible to do. And I think the great developers, many of them here from Portland, because Rust came out of Mozilla, came up with a very good solution with the borrow checker. And so we were trying to fit that into our research. Here's the problem I have, and this is actually the problem everyone has in this region, because we're a semiconductor region. 20 years ago, we had to stop running all of the silicon at the same time in our processors because the chips started melting. A bunch of things were put in place to try and solve this, from out of order execution to speculative execution to everything else. 15 years after that happened, everyone realized that stuff was insecure because they forgot to check if it was secure before they put it in every physical device on the planet. And then someone called my advisor while I was in grad school and said, "Can you fix this for us?" The answer was no, but we can make sure you don't do it again. So that's the problem I'm trying to solve. Here's an example of one way you can understand the application of quality engineering to the hardware design process. I think we all understand here electronic design automation is a big deal. No one could make chips of the complexity we're working with without that process. But it is also not completely mature. It'll probably never be mature. This is the kind of thing I look at all day. This is a value change dump. This is one of the ASCII text-based ways of representing the actions that a piece of hardware takes in simulation at different points in time. On the left-hand side of the screen, I have the header of the VCD file, which enumerates all of the registers in a hardware design. And on the right side, I have the trace data, which represents the different values every register can change to at a certain point in time. One of the problems with this, and it is probably non-obvious by looking at this, is that I have, we were just talking about numbers in a previous talk about like how many test cases there are. Because hardware is made out of physics instead of logic, sometimes there are numbers in registers that are not numbers. That is an X value. That is the binary value X. That is not 0 or 1. And it is clearly labeled as binary because it is prefixed with a B. So this is going to lead to a problem for me. But fundamentally, the way to read this is that I'm working with a piece of hardware. That piece of hardware has a module in it. Perhaps I'm working in a system on a chip that has a network card in it and a memory management unit, and perhaps it has an onboard NPU or something. Within that, there's something called the clock, because everything that we work with is clock synchronized. And the way I can read this and represent this is in ASCII text, I give the double quote as the nickname for the clock. When I apply that as a suffix to a numerical value, that is the value that the clock takes on at a certain time point. Which time point are you asking? The octothorpe prefixed entries in this value change dump represent how many time deltas have taken since the device first turned on. So after there have been 3 distinct time points at which values have changed in a design, the clock is set equal to 1. Why is that? Because it starts 101. And so that is the third number modulo 2. Is this interesting to you? Maybe not. But you know what the kids love these days, and the adults too? They love data frames, right? Because I can take all of that messy ASCII text that was styled in 1989, I think, was when GTK Wave came out. And I can take all of that and I can put that in a Python data frame using pandas. And I think we all love pandas here, right? We love Python data stack. There's only one problem with this, which is that I have to put numbers in this data frame. And I just showed you an example where I had a register that didn't have a number in it because it hadn't been powered on yet. So there was some ambiguous signal or ambiguous value in there. In real life, sometimes things are messy and they don't fit neatly in data frames. So what did I do? I did what every other computer programmer has ever done. I said, well, why don't I just put a -1 in there? That makes sense, right? Everyone knows I can't have -1 apples. And to quote me, I said, wait, isn't that terrible? Yes, it is. Now I need an additional sign bit. What am I modeling? I'm modeling 64-bit architectures. I'm modeling them on 64-bit architectures. And to store a value that can potentially be negative and is of size 2 to the 64, I now need 128 bits, and I've doubled the memory cost in the cloud of storing all of this data. So of course, Intel said, no, you can't do that. Why don't you use not a number? Well, that's the same problem that I have to say what type I'm storing. And so what did I do? I did what everyone else does. I said, I bet I can rewrite this in Rust, and I bet I can rewrite this in the ASF arrow format, which has a nullable type for every type that is supported by arrow. So in the case of the large-scale cloud data systems, my understanding is many of them are running on arrow formats under the hood. Many of them deal with large-scale cases of missing data. So all of the data stored in an arrow data frame on the cloud also has a nullability matrix, which is a single bit for each one of the possible fields in the data frame. This is dramatically more efficient than storing a signed integer, but I do not have a way to address this natively from Python because Python doesn't have a nullable array. So what do? I use the Rust option type. Now, you don't have to use Rust. When I learned about options in undergrad, before Rust was designed, we learned about options in Haskell and we learned about them in Lisp. Do I have any Lisp appreciators in the room? Maybe? No, okay, a little bit, right? Yeah, so I learned about the Lisp option type. So I was looking around for a real language that actually exists, that has a compiler that works, that has an option type in it. And I found Rust. This talk isn't about how Rust is good or why you should use Rust. It's about how some of the safety features and how when you have a language that actually models the underlying system, you can write safe and reliable code much more efficiently. How much more efficiently? I'm glad you asked. So now I can put nulls in my data frame. So this is actually correct. I no longer am claiming registers have a -1 value in them, which is not meaningful. And I can also compare how much faster this is than Python. So in the last 45 seconds, I'm going to talk about speed. I threw all of this stuff in containers and ran them on I ran them in GitHub Actions because I didn't want to pay for any cloud usage. So I would not recommend doing this if you're an actual company with budget. But you can, in fact, run this for free on Amazon servers if you say it's part of a checking in a commit to GitHub. What I found is that Rust takes a long time to compile, but it's not like Python's that fast either because Python is written in C and C is ancient and it is slow. I also found that Rust can make really compressed binaries. My Rust binaries were less than half the size of Python because Python has to run with a built-in runtime. Now, I wrote this when I was still running Rust on a C runtime, and that's not going to happen when I take this to the next step. So we're going to convert this to unsafe Rust and start writing freestanding binaries pretty soon so we can get our container size down. Then, of course, we're going to take it out of containers and run it function as a service, right? I did have an expensive build container, but I only had to use that once, and then I threw it into the sun. I used a 65 megabit data set because I'm an academic and I don't have access to 10 terabytes data sets. So I used 65 megabytes, which is almost the same size. And Rust was 10 times as fast, and I bet that scales probably better than Linear. So I think you should probably buy my product. It's for free on GitHub. You can use it whenever you want. I know you didn't believe that. There's the link right there. That's the source code. If you are a hardware designer in Portland, Oregon, and you would like to make data frames that describe the behavior of your hardware designs, hit me up or just take that code and use it without talking. Thank you so much. Sorry I went over on time, but I had a great time talking to you.